So we look at the relationship among tau, delta theta, and delta W. We know that tau is a vector quantity, and delta theta, being a displacement, is a vector quantity. How is delta W related to tau and delta theta? Well, at this point you really need to know the analogs between rotational and linear motion. And preferably you know how to derive all of the quantities for linear motion, at least for uniformly accelerated linear motion. And derive the fact, for example, that in linear motion work is the product of force and displacement, or the dot product of the force vector with the displacement vector. If you know the analogs, you can conclude what the relationships are for the angular quantities, and then hopefully you understand how the angular quantities are derived by exactly the same details of reasoning that you have for linear motion. Now I say exactly the same details, exactly the same steps, exactly the same procedures. You simply start from this premise that acceleration is uniform, and if it's angular acceleration, everything follows from that the same way it does if you assume constant linear acceleration. All the way through derivation of work, the work energy theorem, and impulse momentum and conservation of momentum. Okay, well, having said that, look it up. Your book tells you. We spent a class, at least a class, referring to this and using the idea. So this is analogous. Well, this is analogous to force. This is analogous to displacement. And of course, work is the work done on a displacement interval is the work done. So analogous to this, we say that tau, delta theta, and delta W are related by, well, product of this and this. And I'm going to say a dot product of these two vector quantities. So there's your work. Okay, now remember, torque, tau, moment arm, cross product with force. Could be in any direction depending on the directions of your moment arm and your force. Delta theta, if you got an object moving in a plane, moving this way in a plane, then right hand rule gives you the direction of delta theta. Got to be perpendicular to the plane of motion at that instant. Use the right hand rule, you get the vector quantities, you can take their dot product, you get the work. Okay, so another one, net torque, time interval, and delta L, whatever the L delta L means. Okay, what's our analog? Well, if this is analogous to force, and delta T, of course, is just time interval. If you know the force and the time interval, you get the impulse. Impulse is equal to the change in the momentum mv. So the impulse is equal to delta P. So F, delta T, and delta P are related. Okay, if you know F and delta T, you can find delta P. Just multiply F and delta T to get the impulse, and that's equal to the change in momentum. If you know any two of these three quantities, you can get them. The analog, and this isn't a rigorous proof, but it works, and then you can make it more rigorous and understand it better, is that tau is analogous to force. Delta T is, of course, just delta T. And then you would want to say something about impulse. And I'm going to put a net on my tau here just to be consistent. Okay? You want to say something about angular impulse, whatever that might be. Now, you can't just call this impulse because torque is not the same kind of thing as force. It's analogous to force, but it's not the same thing. It has different units, among other things. And again, you're multiplying or taking a cross product of a moment arm with a force in order to get the torque, so that angular impulse is not going to be the same as impulse. So this thing that we call angular impulse, we're going to use, well, we're going to call it angular impulse. There's not really a symbol for it, but it's equal to the change in angular momentum, and L is angular momentum. Okay, so this is change in angular momentum, or delta L. And L is the angular momentum, and by the derivation of this thing, and it's very simple, this is equal to I omega. So delta L is the change in I omega. And of course, I omega is very much analogous to mv, right? Because omega is the analog of m, and I is the analog, omega is the analog of v, and I is the analog of m. So we have this relationship that says that delta L is tau net times delta t. Okay? Now again, this angular momentum thing is different than momentum mv. Okay? Different units. You can't add angular momentum to linear momentum. You can't add things with different units. They're different types of things. So they are not compatible for addition. Angular momentum, completely different quantities. And both are conserved in an isolated system. You have conservation of angular momentum. You have conservation of momentum within an isolated system. Okay? Now, omega, moment of inertia, and rotational kinetic energy. This has been smudged a little bit. And by the analogy, since omega is analogous to V and I is analogous to M, then kinetic energy equal 1/2 mv squared becomes kinetic energy equals I omega squared. Again, on a deeper level, you should be able to derive this just based on the definitions of moment of inertia and uniform acceleration. Now, unlike momentum and angular momentum, energy is just energy. Energy is not a vector quantity. So you can add a rotational energy to a linear energy. A system will typically be composed of energies of translation, the energy something has because it's moving through space, and energies of rotation. And of course then you have potential energies as well. Okay, so there is often a little bit of confusion between conservation of energy and conservation of momentum in the first place. They're completely different quantities. They're conserved, but you can't, energy can be conserved where momentum isn't. Momentum can be conserved where energy isn't. Momentum can be conserved, did I say that? Where energy isn't. Momentum could be conserved in a situation where angular momentum isn't. Okay. Now we have another relationship, omega, I, and L, and I kind of alluded to that down here. Omega equals I times L, where L is angular momentum. Take that as your definition of angular momentum. Okay. Then I and delta omega and delta L are related by, well, delta L is, I say I delta omega. I was a little bit careless when I said that. If the angular momentum of a system is, the moment of inertia of a system is constant, then that's valid. But that's not always the case. So I should have said that delta L is the change in I omega, and that equals I delta omega if I is constant. So we want to be careful about that. Okay, now, that's pretty much a conceptual framework for angular quantities, for angular motion, for angular energy. And we're going to move on now to the relationships for simple harmonic motion, which are recent and which people are doing pretty well with right now. Let's try to put this into a broader context. We'll pick this up in the next clip.